just recording this. Hope it is okay with you guys, okay? Okay. So this is my friend Anne. She works in security. So I asked her to be here because she has been a motivator for me in getting in computer security, especially for FIS. So thank you.
Today I get to introduce Stellus, and I don't know if you guys know him already or not. Our illustrious instructor is Stellus Pereira. He graduated in computer studies from the Indian Institute of Science. I don't know if you guys know that, but it's one of the top rated colleges in the world. He did his business management studies at University of Michigan, Ann Arbor. He's been to a few other colleges since. He has over 35 years of IT experience and has even won awards for technical excellence. He's proficient in multiple computer languages, databases, and tools. His favorite computer languages are He's architected and led projects for large international clients, Intel Corporation, and so on. He's been with FIS since 2006. He's been working with default managers at Union Projects Group as the lead designer, and he was the lead architect until June of 2012.
Yep.
Something that y'all may not know is that during this time, 95% of the VM data model from the ground up, that's why services and web pages, have been designed by Stellus. And he led the onshore-offshore team to develop and implement Default Manager. He currently works as an architect responsible for subsystems in Default Manager, also queuing, vendor management, and he leads the team for performance. He has, more specifically to this, over 12 years experience in cybersecurity. Recently has earned a certification to CISSP, which is Certified Information Systems Security Professional, and he is a certified ethical hacker. He has extensive knowledge of encryption and software development methodologies, which was very helpful to the rest of us on the study group, believe me. And I've learned quite a bit from him, and I'm sure that you guys will too. So please join me in welcoming Stellus.
Thank you.
Thank you. It's my honor.
Thank you. Good afternoon, everyone. This session is going to be purely, I'm not trying to say I know many things about security. Going to be more of sharing information. Whatever information I gathered the last 12 years, I'm going to share with you. And give you a brief introduction about my profile. Just to give you a personal story and background, December 17th of 1997, in a cold winter night, woken up by a telephone call, one of my friend Ravi calling me. Other end of the line, my friend said, "Hey, our hospital database is hacked. All the alarms and bells are going on. I don't know what to do." Ravi is one of my good friend, masters in computer studies, and he just got out of the school, and he was interested in getting some job because he was on a J1 visa because he cannot work without a visa. So one of the hospital hired him, and they gave him 1 week training as network administrator. He's a computer science professional, network administrator in the local hospital, and they gave him a bunch of CDs and asked him to install Cisco routers. So he knows a little bit of computer networking, nothing of security. So to cut the story short, at the end of the line, he was saying, "Hey, the database is hacked, and we need to stop the attack." I was new to networking that particular time, 1997, and all I knew that okay, there is a switch going out to the internet, at least you can unplug the, that's the only thing you do. So I somehow told him to locate those and unplug the whole thing. But what had happened is the next day's local newspapers, local hospital database hacked. 300,000 people's vital records are gone, compromised. It was a real dire situation for him. He is just a new guy and he didn't know much to do. And the next day the IT director called in a press conference and said, hey, Ravi has been sent for network and security training multiple times. Multiple times means he was sent to a Cisco router, some class in Chicago. It was a free class. Also he gave a CD instruction installation CD for some routers. So multiple training, yes. Theoretically 2 training he had. So he was fired. Within 24 hours he has to get out of the country, because here in the US, most of you don't know the visa, because you all are Americans, you don't know. If you stay without a visa, you can be put in jail within 48 hours. So being a student having prospects, he said, okay, let me get out of this place. He has to go back. That particular day took an oath. Never in my life should happen to me or none of my friends. So I started learning computer security from there on. So when I came to FIS, I played a low profile on computer security most of the time. And when I was working for another company called CSE, Computer Science Corporation. So many of the application security architecture I have done for Citibank, GM, couple of those companies, at least in the US. That is my background. Now the reason why I decided to do a session in FIS, couple of things. I used to interact. I have programmers working for me. Sometime when we interact with them, during the conversation you realize, okay, he is very new to the transaction processing. Security is very limited. Even though he has some knowledge, he really doesn't know the fundamentals. So that was the reason I said, okay, I can give a brief idea about the security fundamentals, special focus to transaction security. So that was the reason I was wanting to do this class. We will focus only what is highly essential. And this again is just a warning. This was originally designed to Citibank in South Bend, Indiana, 99. I used to work for a company called, as I said, Computer Science Corporation. No part of this presentation is part of FIS documents or anything, so you won't be able to, even they didn't allow me to connect my MacBook onto the network. So he said, hey, it's one of those things which is your own stuff, let's not mix things. So this is my own stuff, but I have given all the handouts. Whatever I am going to explain, you will have the handouts. So if you want to have a reference, you will have those things. One of the things you have to be aware, physical war planes and tanks are not going to do much more. There's a huge cyber security force. I think Obama, and in fact I think Bush's time itself they started. One other thing you have to think about, because every second, because Anne knows, every second thousands of packets of attack efforts have been done by China or North Korea. If you see the firewall, because Anne knows, a lot of bombardment onto our network try to attack private infrastructures or government organizations. So this is a very critical thing. Everyone has to take initiative, at least learning stuff. So as I said, there is a huge cyber security force itself is in progress, and I think looking at the history, I think couple of days back, federal HR database has been hacked. You all know, close to I think 150,000 employees records are breached, or
They said every single federal employee above 4 million.
oh, 4 million. No, I did not know that includes must be the previous employee, not current and previous. Okay. And 2011, 24,000 papers files has been stolen, not paper files have been stolen from Pentagon. So the list goes on. So it's very critical that at least we need to at least understand what is the gravity of the situation. Now, when you say computer security, in the computer security terminology, there are three things they classify. One is confidentiality, the data which is supposed to be known only to a particular person or to a person should remain confident. And next one is called integrity. Integrity is nothing but only a person who is authorized to modify should be able to modify. Third one is availability. Availability means, sorry, I think I went back. When information is needed, that should be available. For example, typically you hear about denial of services because some hackers can pound millions of requests to your web server, and after a certain number of transactions, it cannot hold because it doesn't have the CPU or the network bandwidth, so it will crash. So if that is broken, also is called computer security incident. So just to revise, reiterate, confidentiality is nothing but information is not available to the person who is not intended for. Information could be in case of a war, troop positions, attack plan, soldiers, and any asset details, you know. In your case, personal, okay, social security number if you reveal, and if you give to someone with their date of birth, and someone can go and open your credit card and really make your life miserable. And also health records, that's also very vital, right? Because you know someone doesn't want to come and market you with all the drugs and related stuff because he found out you have a certain illness. So it's personally, it needs to be remain confidential. Obviously, intellectual property for organizations, design, marketing strategy, many more. I'm just giving you some idea about those things. Integrity, again, reiterating, only the intended person should be able to modify. For example, you will have salary records in our HR department on the server. If someone goes and modify your $100,000 salary to 200 or 500,000, you don't mind, right? And if they modify to 10,000, you didn't like it. But at the same time, HR need to have access. Only HR person should have access to those data to change it. So the integrity is only the person who is authorized should be able to do that. If there is a breach, then it is called integrity breach. My clicker is sometimes not working. Okay. Availability, again, as I mentioned, when the information is needed, if it is not available, that is also a breach. For example, you are going to an UAM's hospital operation theater, and the doctor need to check your last medication as well as the interactions or allergies, and that particular time there is an attack on their server, your life is in real danger. You are at stake. So information available at that particular moment is not available, then that's also a breach. So these three critical things are in computer cyber security terminology. This is all classified as security breach. Any breach on these three is called computer security breach. I need to give you at least some vocabulary about cybersecurity. You all coming from various different backgrounds, so some of you may be already aware. So those who are aware, you can just take a breather and wait. Those who are not aware, I just want to run through so that at least when we go into details, you will not be unfamiliar with those things. Encryption, all you all know, just converting your known message into a cipher text or plain text into cipher text. Decryption is nothing but the process of turning it back, cipher text to plain text. Cipher text is nothing but an encrypted text which is not readable by human being. Typically, an encryption decryption process involves at least an algorithm and a key, or sometimes multiple keys. Also, there are two types of encryption. One is symmetric encryption. Another one is called asymmetric. Symmetric meaning you use only one key for encrypting and decrypting. Come on, sorry. Sometimes doesn't cooperate with me, I believe. So symmetrically, only one secret key is used. For example, I want to communicate to Anne. Anne and myself have a secret key between a known only to both of us. That key, using that particular key, I will encrypt a message and send it across the wire. Once Anne receives it, she will be able to decrypt and get the actual message. So that is the symmetric key, the same key used for encrypting and decrypting. Before going to the nitty-gritty details of the encryption, this is one of the fundamental things you should understand. If you don't understand this, you won't be able to do this. 90% of the encryption uses exclusive OR. Does anyone know what an exclusive OR? Can tell me what it does? Anyone who writes in assembler program here? C, you assembler. So you want to give any idea, sir? Exclusive OR. Okay. Yeah. To certain, you answered partially. I think you have two values. You are trying to say if this equal to this, then you say yes or no. So to just remember by heart, is simple approach. If A and B is equal, for example, the first one, then it is 0. If both the sides left and right is 0, left and right is equal, then it is 0, else 1. This has a very big fundamental property used for encryption and decryption. So if you look at it, 0, 0 turn into 0, 0, 1, 0 turn into 1, 0, 1 turn into 1, and 1, 1 also turned into 0. This you have to understand, otherwise there is no moving forward with the encryption or cryptography. Now, I have introduced, I don't know how many people knows hexadecimals, but I think in your computer classes you must have learned at least something about hexadecimals. So typically a byte is, I'll go through the same thing, but it might be a repetition for you, but for the continuation purpose of the class, at least I'll give you some idea. So 8-bit, we consider that as 1 byte. Suppose you have a message starting with alphabet A, ASCII value, which is nothing but 41. And if you look at your handouts, I think I gave a ASCII table, because that you are going to have some exercise, so get familiar with those things. You have an ASCII sheet. If you don't have, you can pass it along. Now, you can pass it along back also. Did you all get it, or you still someone does not have it? Mason already knows, I think. He was just trying to. Yeah, it's here, I think. Yeah. You can pick one page from each. You want something? Which one you want? Alpha? Okay. And you need. I think this is not collated. You can take this and see. Okay. Yeah. I know. So I'm trying to explain a simplest process of encryption. If you see on the top, I've give just for reference this just a number bit position. So 1 byte, as I said, has 8 bits. And suppose our data is ASCII 41. Which will be represented by, if you take from here, this is the higher nibble and this is the lower nibble. So 4 bit together forms the first ASCII character. So if you see here, this is a first position, this is the second position, this is the third position. So 2 to the power of 1, 2, 3. So that is nothing but 4, right? And so 4 here comes here, and here there is only 1. 2 to the power of is 1, 41. Similarly, S for 83. This 8th position, that 2 to the power of 4, 8, and this is 2, and this is 1. 2 plus 1, 3. You might. Pardon? Yeah. The data is represented in binary. But for reference purpose, I have put it so that at least you will understand what exactly I am. Because the ASCII sheet, you will see 41 for A. Can you all check, or did I make a mistake? I think. Yeah. So if you look at the, now try to apply the process of exclusive. Okay. 0 and 1, it is not same, so you have to have 1. Similar to this is same, this is same, and this a difference, the same. So this, can you find out and someone tell me what is the ASCII character for this? Did you find something? I don't think you have something there. Okay, let's say. So this is 4 plus 2 is 8 plus 2, 12, and 2. This is 2, second position, right? Yes, C2. A is 10, B is 11, C is 12. Now try to apply the same logic. Okay, now Anne got this message, XOR result. She has this S value, and she applies this, and you get back the same value, right? You go for 1 to 1 means 0, 0 and 1 is 1, all 0, 0, 0, 0, 0, and this 0, this is 1. This is the funda of encryption. If you can get that, the rest will be much easier. But if you don't get it, it will be a little tough. Sorry. Another function which is used heavily in encryption is you do bitwise shift, rotate towards the left or rotate towards the right for removing the patterns, because when you write text, when you write a email, you have a certain patterns. You say, you start with the, hello, all those things. So in order to get out of those patterns, minimize those patterns, there is another process in the encryption they use, is rotating the bit to left or right. Some of the encryption algorithms use that. Now if you see here, rotate to left with carry. Now this is the original byte, right? So you push this one to here, this one to here, and goes up to the last. So you got the original 7th bit here, right? Since it is with a carry, it puts it onto the beginning. So if there was no carry, that will become 0. This again, when you really start learning the encryption, you will know whether that particular algorithm uses a particular type of rotation. Similar, this towards the left, there is right also there. And also I was wondering, I forgot to tell you, the class, I think what my plan is, every 1.5 hours you will have a break. In between I will go through most of the slides, and I will stop and ask you question. If you have any questions, you can ask me. If you have some questions during the session, you can either write it down towards the end question answer session, you can answer those things. Okay. Typically a byte is divided into 2, that the previous example I mentioned. Right now you understand that the highermost byte is now F, means you have all the bits turned on. Similar to this is 9. Now can someone tell me on the lower nibble what is the value? On the F3. Yep. Now we have done a simple encryption. If you have just a single byte that is 8-bit, what are the number of permutation combinations you can have on one byte, right? So that can be broken within milliseconds, right? You have a message with one key calling 8-bit key, it can be broken within milliseconds. So that's the reason they come up with a large number of bits as a key. So every bit you increase, that doubles the number of CPU cycles, because when you say XOR, exclusive OR, it takes at least one clock cycle, CPU clock cycle, to execute that from the register. I am an assembler guy, so you have to bring the value from the memory, do a second operand, and then do an XOR. So there are 3 instructions. Typically the modern CPUs within one clock cycle, fetch, compare, and store is done. I think Dan, in IBM also, I think the latest ones you have within one clock cycle you can do the one XOR instruction, right? Is it not? Okay. So that's again to do a brute force. These are the terms which will start using it, because computer terminology people will start using those. Brute force is nothing but you are trying all the permutation combinations to decrypt the message. And the bottom point we will discuss later, which is not relevant now. Now, as I mentioned, for an encryption to work, you need a key and an algorithm, right? So these all are the popular algorithms. Under symmetric key, you have AES, that is the most popular now. I think 2002, this was officially declared as the US government's standard for all the advanced declared as advanced encryption standard. You will see many places you will be hearing about AES. So remember that, advanced encryption standard, which has key length, a variable key length, that is, you can have 128, 196, 256 bit. This is the maximum you can have for that AES standard. Prior to AES, there was an algorithm called DES, Data Encryption Standards, and initially it had 56 bits length, and then they converted into, make it a little more harder to crack, it converted into 2 DES and then 3 DES. 3 DES till I think 1999 I think they are using some. Now some other places it still uses the triple DES even though the keys are broken, but in some of the organizations they still use, because it takes time to convert the applications, so it takes time. Originally it was designed for NSA by IBM. Blowfish, Twofish, Serpent, all those things open source encryption standard. And in asymmetric key, that is a public key, private key, that you use 2 different keys, the most common is RSA, and I think even elliptical curve also is being used in many places. That some of the routers, I believe in our class, I think you remember, routers uses ECC because it is easy to implement at the hardware stage. RSA and all need a lot of computing power. So this two, if you can remember, that could be good enough. RSA and elliptical curve. Now, when I want to communicate to a person, at least you need one key, right? Suppose I am trying to communicate to Mason. Between myself and him, at least you have to have one secret key. What if one more person comes? In this particular case, Bob and Alice is trying to communicate. He needs at least one minimum key. And when a third person is introduced, you are getting 2 more keys because they need to communicate together. So in this symmetric key, there are 2 major issues. One is, how do you distribute your key? You cannot all the time call and tell, and today I changed my key, tomorrow you'll have to start using this, right? And suppose you have hundreds of ants every day you need to communicate, you'll be just only calling them and telling them this is what you need to do to change my key, secret key for decrypting the message. So that's not scalable. Also, the formula, if you look at it, suppose you have 10 people communicating. Can someone tell me what is going to be the number of keys? Okay. How about 100? He used to be a professor in one of the colleges. I am trying to give him a hard time. Okay. Yeah. So it becomes so huge. Again, generating those number of keys becomes difficult, right? So at least you understood what is the place of exclusive OR in encryption, and you at least came to know about 2 types of encryption, that is one symmetric key and asymmetric key. And for an algorithm encryption to work, you need to have a key and an algorithm. That's all. If you can understand, I think you get at least the initial foundation of this class. Now I need to give you an exercise. I think you might enjoy this. Okay, there are 2 sheets. One is the message sheet, another one is the page 1 and page 2. Or you can pass it on. I think you all can take this and pass it on. 2 pages each, you can pass it on. what I want to do is on the page number 2, write your name. No, yeah, first you write your name, and since I don't have enough space, I've said, okay, we'll limit our message to 3 characters and message your secret key to 3 characters. So from here, this side of the aisle, I'm calling it as a logical aisle, you will communicate to the end person. Okay, so you will have 1 secret key. Can you write your secret key on your page and your name and give it to him? Similarly, you to him. All of you can just pass the secret key. Yeah, yeah. Write your name so that at least, is anyone out of not having pair, or I think you will not have anyone, I believe. You can give to someone on the back. No, I think 1 person communicating is good enough. Similar to that, from here you can communicate to give your secret key to them. Similarly, you sir, you can also give to the last person, Dan. Middle guys will communicate each other, middle guys. Yeah, the next one. Yeah. So this is a typical handshake process. For initially, when you communicate, before communicating, you pass on a secret key, 3-character secret key. Let me see what secret key you wrote, just only for the purpose of checking. Okay, so some people write in capitals and some people write in small. So you all have a ASCII table also, right? Now choose a message, 3-character message, each you are not going to tell anyone. You will write the message alphabet on this. See, the first character you will write over here, right? For example, you selected A, capital A. Then what will be the bits for that? That will be 41 means, yeah. So you'll write 00, 1, 00. And the next character, suppose you selected B, you will write B here, B will be here, and corresponding ASCII bits for that. Then third byte you will write here. One person gets the key. The purpose is, the exercise is, he writes a message encrypted. He is going to get only the bottom portion. For example, I forgot your name, sir. Michael will get the bottom portion of this thing. He will have only this. I am going to give them exercise. So he is going to. So you are going to write the message, then the key, and you will, Mason, you will do an XOR and put the bits here. Did everyone understood what it is? Go ahead. 3 characters. No. Name you can put any name, but the key what you are using. This is your. See, yeah. Okay, that's a key you are giving to someone, right? Who is your pair? Yeah. Okay. So what we need to do is, you choose your message. This you are already given to him, right?
No, not
yet. Yeah. So, yeah, you need not do anything because only one pair we are trying to work out. Okay. So you are trying to send a message to him. So you will write. You will select some 3-character message. The key is different, message is different. You will write the first alphabet of that message in here, M1, M2, M3, and find out the hexadecimal equivalent and find the 0, 1 and put all those things. It's difficult, but if you look, you could go. Okay. Sure, carry it. Not okay. Not okay. Sure. Thank you very much. Appreciate it. So, did anyone stuck, or you still have problems? I made only 3 characters, so to make it time. Okay, go ahead. Sure. Okay, go ahead. No, this is the letter. For example, you write a message. He is going to write a message. A, if you write, this all are the bit position. So, what is an equal? A is ASCII value. I mean, A, capital A. There is 41. How do you write 41 in hex? 41 in hex is, this will be 1. No, 4. Okay. This is a higher nibble, right? So, 1, 2, this. This is your 41. This is 4, right? See, ASCII value of A is nothing but 41, right? Okay. So, how do you put that in byte? 0, 1, 0, 0. And 1 is nothing but, right, this is 41. Right. Now, your next message, suppose you are trying to tell him act. Okay. What is the next character? This is C. You will find the next character is nothing but 43. You will encode that here. Understood?
Yeah.
T.
Well, I don't remember how to convert text.
Yeah. See. No, that I'll put that how to convert it on. See, the byte is divided into 2 nibbles, right? Byte is divided into 2 nibbles. Simply, 4 is the first nibble. How will you represent 4 in a hexadecimal? This is 2 to the power of 1. That is the first position. This is the second position, the third position, and fourth position. Okay. Like that, you'll have to write. It's tough, but this will give you a fundamental understanding of how the encryption, at least in plain terminology, it works. You are done, I believe. So, I think Mason was the first one. Brian did the first one. So, anyway, you encrypt it and give to the other person. Now, let's see whether he is going to decrypt and tell me. Did you understand how to do that? XOR at least understood how to do a exclusive OR. Okay. So, this is what he wrote and gave you, right? Okay. Now, the key what you have, you put it accordingly, right? Now, do a XOR. 0, 0 mean what? Is, yeah. No, 0, 0 means 0. Yeah. And once you get that, you have to find out what is a hexadecimal representation of that particular byte. The bottom portion. This is the value you are going to give them. Now, first person, he is using this for him to write the details. Key already you are given to him, right? So, all you are trying to do is, you give him this encrypted message on the 0, 1, 0, 1, 1, 0, 1. You will give. You are not writing the actual message. Sorry, you shouldn't be. No one cheating, I believe. Don't put the message here because I put star star. Yeah, this is for which one is our reference? This is the person who is encrypting it. So he will keep this portion, but after doing that, he is writing the XOR result on this particular portion. This is what we are tearing it and giving it to someone, right? So who is the first person crack the code? Brian, he is decoding it. Okay. Anyone who has done, you can tell me. Done? Okay.
The message is at, I believe.
Can I see it?
They made it a little easier as
The same.
That is cheating. You didn't send any message then. It will be zeros, yeah. But the exercise at least made.
When you put it out in the open, no one thinks it's secret.
Yeah, you're right. So who is the next person cracked the code? Okay, who is the next person cracked? What happened? Okay. Anyone want to share the result and challenges, whatever you had? At least I know one person cracked the code. Who else is the next one who cracked the message? Message. Huh. What happened? What happened? So what was? Show me your sheet. XOR problem. Okay. So what did you learn? What did you learn then? The logic was XOR exclusive or applying it to you made a mistake or you didn't? Ah, okay. So his mistake. You are perfect. Sorry. By the way, he used to be a professor, so that's why sometime I used to pull him. He used to teach in which college? Hendrix, yeah. Computer science. He used to teach. He works in my team. He is also a cat. Works with me. Oh, is it? Okay, that's we are interested in the polynomial equations or prime numbers. Okay, we will come that. So is it your math major or something like that? Oh, okay. From oh. Okay, so that's a good subject. Yeah. Lot of factoring, prime. A lot of number theory. Yeah, number theory. Anyone else want to get the message, or you all? I'll give 5 more minutes if it is. You cracked it or no? He's cracking it. Okay. Okay. So what we can do is I'll give you another 5 more minutes if that is okay. Or because if you don't understand this, there's no point for moving further because everything is dependent on this XORing. Okay, let me. If you go to the handout, you will see that page number. What is in the handout? What is the page number? No, it's not like that. If it is equal, 0 and 0, 1, 1, always 0. If it's something different, turn the bit on. That's all it does. It's all done in a simple transistor logic, flip-flops, right? So 2 cracked and oh, is it? Can I see it? Okay. So what was the message? FIS. Wow. Okay. The key used was AFK. Okay, Brian English. Okay. Thank you, sir. So 2 done. You are also done, you said, or you're struggling? You need a faster computer, I believe, right?
No,
Where are you stuck?
Seeing the message.
I think
I'm doing it. I believe I'm doing it right.
Okay. What is the key? What this you are trying to give to them, or he gave you the this is your card? Is it okay? And this is the key. What he got? PX. 7.
Okay.
Okay, where is P? What is capital P, right? 50. 50. How do you write the 50?
0, 1. 0, 1 is 5. And 0, 0, 0, 0 is 50.
Yeah.
Okay.
This 1 and 4 together 5.
5 and 0.
Zeros, okay.
Okay. And then X, 58. 5 and 8, 58. And then 7 was
Are you sure this is
0, 1, which is
2?
4.
You got the last two letters, right? For sure.
No. This is what is bit position. This is. I had a PowerPoint presentation. I am trying to search for the. See, this is what a byte is divided into. Yeah. So this is the first position. If it is on, this is nothing but 2 to the power 0. Sorry, that is 1. Yeah, sorry. 1. So this is 2, 4, 8. So you are writing that 1 bit. I thought it is different.
1,
Okay.
0, 4.
Okay.
4 and 1 is
4 on. Okay. 4, that's fine. So 5,
Yes.
5 and 8 or 58. So where are you missing that? You said you still have trouble.
I think I'm deciphering wrong.
Okay, so then let me put the XOR separately here. Okay, so thumb rule, yeah. Thumb rule is if both are same, 0. If both are not matching, 1. That's the simplest thing to remember. Say that again. Okay. Yeah. Yeah, I am coming to that. I am making the fundamentals very clear. Now we are making you understand 1 byte encryption, 1 byte. That's all. We'll come to the more complex how to split the message, key length, and all will come. But you have to understand the fundamental first. That's why I don't want to go rush through. Can anyone tell me which page it is? I don't know. I didn't number the page. At least someone, if you want to refer that. Hi. So if we can understand the exclusive OR page number, which is the page number, man? 3 or 3rd or so. When you want to decode, use that particular logic. Okay, if the bits are same, then it is 0. Result is 0. Bits are not matching, whether it is 0 1 or 1 0. That means result should be 1. So exclusive OR plays a big role in encryption. So we were doing an exercise of sending for Mike. I think Mike is one of the architects working in this company for almost 30 years, I believe, right? 35 years, 30 years, 25. Sorry, I'm trying to make you a little older than what I think. Sorry, thanks. So as I mentioned, symmetric key has 2 major issues. One is you have to have 1 key per communication, right? Suppose I am always communicating to Brian. Between Brian and myself, you have to have 1 key. And suppose I want to communicate to you say Don, and I need another key. So the larger number of people keep on coming into the network, you need to create a huge key space. So many keys you have to generate. Maintaining key, that's a big problem, and it cannot scale. For example, I think 100. How much? 100 people. How much did you? Yeah, those goes exponentially. So that was the reason I think the public key cryptography came into picture. Public key cryptography initially started with RSA. That's I think I forgot the name. It's difficult to pronounce the name of the person who came up with that. The fundamental properties of public key, private key encryption is public key. You have two pairs, which are all large prime numbers. The beauty of that key is encrypt with a key, you can decrypt only with the next key. Suppose you are encrypting with a public key, only the person who has the private key can decrypt. So, comparing the symmetric key, you got rid of the key sharing. You will have to send it across. Okay, you have to send it to a particular person. Hey, secretly I'll have to call Brian and say tomorrow onwards my key, use this. Those we got rid of those process. So you don't need to share your private keys. All you need to share is your public key. Anyone can encrypt, and when you want to send a message to you, I encrypt some message and send it to you. You can read, only you can read, because you have the private key. You don't share with anyone else. That is the beauty of private key, public key algorithm. The fourth thing which we need to be aware about is hashing, message digest. I explained you, give me a second. I explained you in the encryption there are 3 or 4 fundamental things you have to know. One is about the keys. You have to have a key or keys, pair of, in case of asymmetric key, you have to have two keys. And you need to have an algorithm, whether it is DES or in case of asymmetric, you say RSA or elliptical curve. Those things are the 2 preliminary things you need to have essentially for encryption and decryption. Third one is called message digest or hash. Why hash is just nothing but a checksum, something similar to a checksum. You take a large number of text and crunch through a function and come up with a magic number. The most popular message digests are SHA and MD, message digest. SHA used to have SHA 1, 2, now I think we have 5 also. Those are the bits which it produces. It takes an input and runs through the hash function and comes up with a hexadecimal number. 128, 160, 190, whatever key magic key length you are trying to, bit length, not here key, is bit length. Someday my clicker is not working. This gives you a little more details. MD2 was the initial one, which again had some key collisions. Again, now you will ask me, you are introducing a new word, what is key collision? As per the message hashing mechanism, no two different texts should produce the same result. That's the whole funda of that. It's just as good as a signature. If even one bit is changed, then the resulting value should be message digest should be, hash value should be different. SHA 256, I think on Chinese lady ran a huge number of text and iteration, and she came up with some key collision. So some of the organizations start using 256 now. SHA 5 is being used, I think 512 bit. It takes a lot of computer processing because he has to go through a large algorithm, going through individual byte, pass through a function, rotate and shift. I think I have a diagram on MD5, I believe. Yeah, this I am not going to explain you the details. Come on. essentially the 4 bytes are taken, depends on the algorithm. I'm just giving you. It runs through a function, then I think it is OR, then do a rotate left, and then the bits are exchanged. So this is a function. I think it is. If you go to, I don't want to go through the individual details. The symbols are given here. You can go to Wikipedia and read that. I need to cover more slides, so you can just do a MD5 Wikipedia. It will tell you how the individual bytes are taken and the calculation is made. The fourth item, very important, is your encryption strength, or the strength of the encryption depends on the session key or the token you create for encrypting. So there is a random function, R&D function, random function in Unix as well as in Windows. There are a couple of popular pseudo-random number generation, cryptographically safe they call it. That's why CPRNG, that is cryptographically random number safe, cryptographically safe pseudo-random numbers. You cannot create a real random number based on any algorithm, then becomes something related to an algorithm, right? But I think it's pretty close, cryptographically safe. There are 2 popular algorithms prior to 98. I think prior to 2010, Windows used to use Yarrow. I think Yarrow stands for a Chinese word, I believe. I don't know. It generates a pseudo-random number which was cryptographically safe, but some people found some vulnerabilities, and Bruce Schneider, I think you all heard about it. He is one of the gurus of cryptography. He came out another algorithm currently in use, Fortuna. There is a very old algorithm for pseudo-random number generation, also popular in some of our old cell phones and some of the routers for encryption. They use this blum shub. One of the encryption is not very popular, but it has been there for a long. So some of the, I think I am supposed to close this before I was supposed to tell everyone and I forgot, I believe. So in Unix or Mac OS, just to test, you say device/random, you check, you will get every time a new random number. And in Windows, there is a API called RTL Gen Random. Again, most of them gives you a reasonably safe random numbers. So key generation, because right now in your exercise, Mason just wrote cat. That's a very popular word. A dictionary attack can immediately, within second, his message will be broken. And so creating a session key is very equally important. If you generate a number which can be guessed, because some people do analyze they try to analyze the Windows 2000, they go through various permutation combination and look at the pattern in which the numbers are generated, then try to attack. Windows 2000 had vulnerabilities and XP had vulnerabilities, and DOS, I think we gone through about the 64, the bit lengths. Okay, now comes the hero, the AES. That's I've been talking about. This is the algorithm which is being used, very popular as of now. It is very strong. It supports 3 key lengths: 128, 192, 256. These 3 key lengths you support. We will, before going to the I think details, I think we will take a break now. Is everyone ready for a break? It's a very dry subject. I would prefer to have break. Okay, then we will meet after 10 minutes. Thank you. Sorry, you are wanting to ask me a question.
Stellus, I wanted to ask about the private key. So it is not going to change, right? We cannot change the private key.
No, private key never changes.
So that is
Public.
what was done in, examinations in Andhra Pradesh, where private key was with the colleges, and they used to send the question papers, and they used to encrypt using the public key.
Okay.
So that way, encrypted question
message.
papers used to go there. Like,
Wow, okay. Now, are you at least getting some idea? What is, it should be useful. You are spending some time. Yeah.
I was keen to know about that, which I asked earlier, like the 8-bit. Now, how we do with 16?
Yeah, we'll come.
32, 64?
Yeah. So the message will be split it into key length. Then you XOR it. Yeah. We'll come to that.
And how the keys are being.
Okay, then welcome back. If you all are ready, I think it's almost 10 minutes. I said I will give you some time for you guys to ask questions. So this is the time you can ask questions whatever we covered. Ram Babu asked me a couple of questions. I've told him that his question was, you're talking about only 1 byte. How do you have a large message, how do you encrypt those? How do you put in the chunk? I told, hold on those questions. I'm trying to explain you in the next few slides. Anyone else has any questions? No? Okay. No question means everything is understood or nothing is understood. AES, Advanced Encryption Standards, as I mentioned, this is one of the most recent and very strong cryptographic capabilities, which is a block symmetric key encryption. That means you can encrypt only with 1 key, and the same key need to be used for decrypting. Now, why it is strong means it has 4 processes to diffuse the bits so that it is beyond recognizable. So the first is called substitutions. It substitutes the actual the data with something else, and then he reorganize the rows, shift rows. Then third is mixing columns. I'll explain you the whole details in individual steps. Fourth one is key addition. Towards the end, he adds a different trick to remove all the common bits, so that at least even if you do message analysis with successive steps, you cannot find out what exactly was the previous step. So these 4 steps makes things really tough to do any cryptanalysis and derive the message in the encryption scheme. As I mentioned, there are 3 key lengths it supports: 128, 192 and 256. And each key length has a particular number of rounds. I'll explain you what that rounds. That essentially it starts with the data, does this particular 4 steps, again the same result is taken, again we go through the next, like that 10 times or 128. So it really diffuses the data, is beyond recognition. And as per the current estimates, I think it is 128 bit, I think, to do a brute force attack with a Cray XMP, it will take 1 billion years. That's what is said. So if you are alive 1 billion years, I think you can get those numbers. Again, that is with the current processing capacity. Say that again. Similarly, when you encrypt, you have to have a reverse process to decrypt. There is inverse of this substitution is done, also inverse of shift is done, and in the reverse order. It starts with the mix column, it starts, then goes to shift rows, then no, it starts with the key adds. Okay, key add was the last step in encryption, so you'll start with this, then goes to this, then comes to this, and comes to this. And I think I need to change the diagram, but essentially it is a reverse inverse operation. Then only you can get the value, right? Now you all know the exclusive OR, so you can start thinking in that terms, right? Now answering Ram Babu's question, because the typical message is not just 1 byte, you need to know, so there will be a bulk data you are trying to encrypt. What do you do? So based on the key length, what you decide, the key length contributes to the strength of the encryption. So typically for 128 bit key, if you select, which comes to divided by 8 means 16 bytes, right? So that will be the chunk size taken as the message, and it passes through all the stages like keep, block substitution, S block substitution, then goes to the next stage of shift rows, mix columns, and add keys. So a block is taken and those are applied. Always, it doesn't matter the length of the message, always it is chunked into the exact bits length, because that's what it is. Just like XORing what you are done, you took the message and put your XOR 3, because in our case what we are exercised is 3 bytes, that is 24 bit. That's what you did, right? Message was 24 bit and your key was 24 bit. Yeah, I think 8 bit. No, 8 bit into 3 bytes you wrote, right? What was the message? Secret key. 3 bytes. Mason wrote CAT. So that becomes 3 bytes. 8 into 3 is 24, right? So 24 bit was the key length. Just for simple algorithm, I'm just trying to give you. So the message is chopped into the size of the key length, and then passes through all the steps, and then you derive the ciphertext. Here actually you might get confused on this mainframe and all. For all the practical purposes, 8 bit is the standard everywhere is used. Even though it reads in 16 bit in the through the registers, 8 bit is a fundamental unit for all the purposes of computing. But when you take 128 bit key, 16 byte is all taken together. But some of the smaller computers cannot handle 16 bytes, so it will split it into, for example, 32 bit computers. You cannot handle more than that. Then they will divide those and have an algorithm to manage that. But when you want to implement the logic, it will be always based on the 16 byte for 128 bit key length. For this encryption, there is no always it is bits, right? Whether you stretch into 2 bytes, 3 bytes, doesn't matter. Encryption is done at the block. 16 bytes are taken together, and on that bit level XORing is done. Simplest example what you have done. Did I answer your question? You still have doubt about it? Yeah, for example, a message for let's write. Yeah. Yeah. No. Yeah.
So in this, does the name get represented in 8 bit or yes,
No, sorry. I think he has a genuine. He's having a. In the encryption there is no conversion. These bits of data, whether it is A, B, is all 0, 1, 0, 1, 0, 1 on the byte. That's all it matters. It doesn't matter whether it is A or B or something. It's a bit pattern, right? When you type in on the computer, 1 byte is reserved for A, right? 8-bit. That is what's stored in there. So it doesn't matter what character is stored. It is for the encryption purpose. It is just bits. Only thing is we are chopping the whole messages for the purpose of encrypting using the algorithm. So algorithm, when you select 128-bit, always 16 bytes will be taken together, and the encryption algorithm will be applied. When it receives back, it decrypts and gives you the whole string. If it is a readable simple email message, you will get an email message. If it is a data data with you say for example COBOL COM3 figures, it will be bit by bit. As far as the encryption is concerned, there is no particular displayable or non-displayable characters. It's all converted into bits. Got it? Okay. Anyone else? Yeah. There is no standard as such. Again, that depends on how critical the message is. If someone want to crack your message and take you $1 million, how much worth that your encryption strength should be, right? It all depends on the criticality of the message. If you are just simply sending one simple message, you can go to the lowest 128-bit key. That's the lowest one available in AES, encrypt it and send it across.
My question is, say the key is 32 bytes, but my message is
32, okay.
1 byte. What would the standard be?
Oh, okay. So then it is padded with additional trailing space, and it will be taken care by the, not space actually, it's taken care of the encryption because there is a padding mechanism. Suppose you have, for example, any message, it will not be exactly at 16th byte. The last one definitely will have some spaces left because there is no 16 byte. So there is a padding mechanism. We can go into that detail. That itself will take an hour, I believe. But there is a padding mechanism. When you send it and when you receive it back, it will unpad that. It's all taken care in the algorithm, as well as some formats which is described in the individual specific algorithms. Understood? Or typically people don't send any 3-digit characters or something. It will be always large. Okay, and this will look bit confusing and complex. This is what the process AES follows. As I said, there are 4 stages. This I have taken the 128-bit key length. So what happens is you get 16 bytes. The first message is taken in order and split it into 16 bytes here. And as I said, it is the first step is substitution. There is a S box. Sometime you might hear when you read computer cryptographic documents, you will see S box. S box is nothing but a substitution, which was there in which is used in many cryptographic functions like DES or triple DES, or even Blowfish, Lucifer. All those uses those. I will explain you what a substitution box is, S box is. So the byte is taken and it is substituted and you get another value. I'll give you a run through of these steps, then you can go into 2 steps details what exactly is being done, just for the clarity purpose, so that at least you understand what it is happening in the system. So first is substitution. It takes some value, looks at the bytes value and substitutes with another value and puts it there. And shift rows, now you have 16 bytes at a time. It does a shift row method. For example, B1 goes here, B2 goes here in this block, and B11 comes here. I have not drawn the whole thing, it's just a partial thing, because if I draw the whole thing in the initially I draw the diagram and it was so confusing, I said let's not do that. So if you want to go very specific, you can go and read the white paper. It will give you which box goes where. So essentially this reorganize, shifting rows. Another one is mixing columns. So from here to here there are columns are getting mixed. That's also another one way of diffusing the message. For example, when you write attack North Korea, so the first byte will get transferred here, and the second byte will come here. So the order is disorganized. So a dictionary attack cannot find out a word from here. If the message is in a particular order, you can find out, okay, North Korea, North, after N there should be O. So there could be inferences and derive the text. So in order to avoid that, this shifting is done. Also towards the end, a additional noise is added. It's called key addition. So there are 4 stages. This is bit difficult to understand. I think I took at least possibly 4 weeks, I think, in studying for this, is because sometimes you have detailed questions about what happens in mixed columns, what goes where. These all are the exams. So if you don't know the answer, you have failed. So you have to study that. So it's difficult to understand, but I think I am trying to give you a gist of it, at least, so that you have an idea how things are diffused, so that it's beyond recognition. That's the whole purpose, right? Now about the S box. S box is a fixed set of values. 256 values are put on one box, and based on the input it goes by rows and columns. For example, if the plain text message was secret, the first character is what? S, right? What is the ASCII value of S? Is 83. So where does that fall? 8 here, 3 here, right? This particular position. What is the next letter? Is E, 69. So this goes to 6 and 9. Now there's a particular value, it will pick up that for 2 bytes. If you want to do that, the ciphertext becomes the stage B. This becomes EC and F9, 2 bytes. I'm just showing you the sample, okay? Let's go back to this thing. First stage is take the message, run through the substitution box. That is, S stands for substitution box. It looks at the actual value of the input of the first byte, assuming that the message was secret. S is the first character. It goes 83. 8 is the first position because this is a matrix, right? 8 and 3. Oh, sorry. Then you'll change that. I think I made a mistake. Just look at the S and tell me. This is what? Okay, I think I made it. a typo. So it should be and E69. I don't have the ASCII chart. How did I miss that? It was all decimal, I think. 45. 45. Done? So now how did I arrive at E and C based on the previous value? I used the standard S box from AES there is a S box published. See, this is the actual value which is used in AES. So that values you, for example, I think I must have the value what I had was 8 here. You know what I'm trying to say, right? I couldn't put the same values on the same grid because it was taking so much of time to type in all those things. Essentially, your column row, you find the actual value from the actual message, take the first byte nibble and put it on the column and put it on the row, and you get the value, and that is the value, put it on the encrypted message. Got it? And shift rows, even though it's shown like this, is a little more complex than this, but essentially the rows, the data is made into rows, and that rows are shifted. I will try to give you a little more details on that. I don't know, in the back you won't be able to read, I believe. So suppose you have 16 bytes with the 128 bit key, 4 by 4 matrix is formed, row column. Okay, that's the input. And the first row, there is no shift, you don't push that. But the second row, you will shift it, just like as I said, shift towards left. So the one which was here just pushed further, right? Shift to I think it is something is odd here. Anyway, to give you an idea, only one shift will be done, one block will be shifted, one byte will be shifted, here will be 2 bytes will be shifted, and this will be 3 bytes. This is the third step in the AES encryption process. If you don't have to remember all those things. There are documentation. Again, the purpose is to diffuse the message into a undistinguishable, recognizable form. Mixed column and key addition is a little involved. It takes at least 20 minutes to explain the whole process. So for that reason, I am not explaining those. That's the third and fourth step. Blowfish is one of the algorithm which is being I just want to mention this is one of the symmetric key algorithm is very popular, written by Bruce Schneier. He used to promote that. It's also a very strong encryption. It was, in fact, with RSA, he had also come up with its own algorithm. But just to mention, he is a big figure in computer cryptography. Now, one more thing I want to give some classification. Some of the symmetric encryption algorithms are used in two different ways. One is block encryption. In this our AES, you can only go by the blocks, right? 128, 256 or 198. What is the numbers? I forgot. Okay. those are in blocks. But some of the application like cell phone, you have to have an algorithm which is stream ciphers. That means as the byte comes in, you should be able to encrypt and send it across the line. Otherwise, if you are using through a voice line, you'll have to wait for the 16 bytes. Okay, when you say Mason, May something, you will hear, and then you have to wait for the next 16 bits, right? 16 bytes. So some application needs a stream cipher, some can work with block cipher. So there are various encryption algorithms supports block ciphers and stream ciphers. RC4 is one of the most popular, which is used in cell phones and stream encryption. In addition to this encryption, in general, for example, in DES or triple DES block encryption, you have additional encryption processes called block cipher chaining mode. For example, you take 16 bytes, do encryption, and the result is taken, used as an input to the next step in the process of encryption. So it's difficult. I think it will be difficult for you to really look from this. I couldn't draw the picture, so I have just taken a screenshot of it. Essentially, a plain text, the block 16 byte block is taken, and the initialization vector, I think for your understanding purpose, just a random value is added so that it diffuses the text characteristics, and then it is passed through the cipher mechanism, and the result is called ciphertext. That's the first cipher block chaining, and that result is taken and used against the next block. Suppose you have a message of say 16 characters, you have the LD message, and that is XORed, that is exclusive ORed with the next block of the message, the next message first. Then it passes through the next step of encryption. So this is called cipher block chaining, CBC, cipher block chaining. So this continues till the whole message is done. So by the end of the message, you will have no way of knowing what was the message. Even if you do cryptanalysis and reverse engineering, it takes a lot of computing power and a lot of guesswork you have to do. So similar to this, there are multiple cipher block chaining algorithm, but it is used mostly. This is used in data at rest. For example, you store Oracle, for example, it saves data, encrypt their file systems. So you have to have a faster algorithm, but at the same time, because you have a large volume of data, then you can do a lot of frequency analysis and find out what, because in Oracle table you always have, you say customer ID, then you have a customer name. So there are a lot of possibilities in which you can guess what could be in that particular column. So while encrypting, they use this kind of stuff for a block of encryption, so that at least you cannot reverse engineer and find out the actual value. Even if someone copies the whole block, you will not be able to find out what the data is unless they get the key. So this is being used there. And another one, there are 4 types of cipher block chaining. There is another one is cipher feedback. This is also used in some of the application. Again, the method is a initialization vector is taken and that is encrypted, and the result is XORed with the plain text, and the ciphertext is taken as the input, passes through the encryption process and XORed with the plain text. This one I think is cipher feedback has less error prone, because if anything, any block of encryption function fails, you have some way of recovering. I think CBC cipher block chaining, is difficult to recover the data. So one of those modes are used for data at rest storage in your standard disk or something. Now output feedback is a little bit different. I don't think you need to know, but again something similar to this. The difference here, I think it is initialization vector key encrypts through the whole thing, and plain text is taken, and plain text is XORed with the cipher text of the initialization vector. Is a little bit different than the cipher block chaining, bit different. I don't off my top of my head I don't remember what this application used for, but this is also there, OFB, output feedback. Counter mode also is something similar to that. Essentially you are using the previous block's result, also part of the encryption. I'll stop for 5 minutes, and if you have any questions, I think it is, you may have some questions. I'll give you 2 minutes if you have something to ask. Otherwise, because a lot of stuff I am covering, like okay, I went through the 4 levels of stages of AES, substitution and shift. Pardon?
Getting around, actually shifting through it. What is the what are they doing to kind of keep it from actually returning back to what the original message would be?
Possibly, yeah. That will be really surprised, right? To the original, after decrypting, you have the original message. Yeah. One of the beauty of S-box, I think it is S-box is substitution box is created using a I think inverse polynomial one function, which takes, I think I have a slide in a detailed presentation, I think I have. So the S-box makes sure that it will never go back to the original. Okay. The simplest way to test that is just change the S-box with the same value. Understood? Then you know the whole thing is working or not. The S-box for this is that case mathematically computed for yeah.
And he knows the key then.
Key he cannot do with the whole purpose of key.
What is the purpose of all these patterns and all that? Because when he knows that if it is AES, then he will apply the same patterns again to get back.
Yeah, but the algorithm is designed such a way that you cannot reverse engineer just by looking those patterns. So it is.
Only the key is important. If you know that it is AES, okay, you can reverse engineer quickly.
Yeah, that's why I think it is. You'll have to read more on that, but it is well tested. I'm not saying it is unbreakable. You can go through a lot of permutation. Brute force attack, yes.
As of now, what I am understanding is like the patterns which you are applying in AES, the same would be applied to reverse engineering if you know it is AES.
Yes. Yeah, it's a good question. Yeah.
I think the whole point of the substitution and the shifting is so that if they intercept a message, like going back to the World War II and the German Enigma machines, they would use plain wording, letter encryption, they'd do it the shifting. So you could just match the patterns and look at it and then eventually decipher the pattern that was used and reverse engineer the key. When you do all the substitutions and mixing the shifting columns, everything what you get at the beginning is so garbled, there's no way you're ever going to be able to reverse engineer a key out of that. So that's a lot of substitutions. And if they know the algorithm, if they know the keys, then they have the keys to the kingdom anyway. And they can just follow the reverse process.
As a substance, we won't find out how this is. Changing the message.
Yeah.
Because it's different garbled.
We have a fusion today that you can take the original message, like
Yeah.
you take the original message and look for patterns that appear in the situation. So as soon as you drop the fuse, there's no pattern.
That's what got in World War II with every single sign-off that held Hitler.
Yeah.
So eventually they found that, and they found that in the pattern where it went.
Morning weather report.
But it scrambled the whole thing at the beginning before you decipher it. It's going to be much more difficult to find any patterns to help reverse engineer.
And you can really with the pattern because of the frequency sector that show up. So they knew they're doing the past, they're doing the pattern, weather,
Yes, yes.
the gazillion of whatever.
Imagine, yeah. Any more questions? So, to reiterate again, in public key cryptography you have two keys, right? One is kept private and never disclosed, and one is given public. That's why when you want to buy a certificate from certifying authorities, who is the biggest CA? VeriSign. When you go to VeriSign and ask, and hey, I am Mr. Brian English, and I want a certificate to host on my computer. So they will verify your credentials and issue a certificate, which has a private key and a public key. They comes in X305. What is the format? It comes in something. Yeah, I don't remember that. But you get a certificate, which is given with a encrypted password. Only is given to you. So when you import the certificate using key import, key store, and put it on your system, those values in the operating system safe key storage. And anytime when you are communicating or using your certificates, essentially you are using the public key infrastructure in your PC. So when you receive a message, someone, for example, Matt encrypted a message and he was wanting to send it to Brian. So Brian's public key is published to everyone. If you go and ask the VeriSign, hey, what is Brian English public key? It is given to everyone. And Matt encrypts the message, and only Brian can decrypt it because he only has the private key. That is in nutshell, that's a public key, private key. Just for confidentiality mode, because no one else can derive the key from the public key. That's another big feature of RSA, public key algorithm, or even elliptical curve. And also another big advantage is you are not sharing a private key, so thus minimizing the probability of someone getting your key and decrypting your message. So it's a very strong algorithm which is widely used. The issue with that is computationally very high intensity. For example, block ciphers, if you compare 128-bit block ciphers and the public key, you say usually start with 512 minimum bit on this public key, private key, and it's almost, I think, 100 times slower compared to the block encryption. So I think one another thing which you might see in people when you are talking about cryptography, the most secured key what in cryptography what they call is one-time pad. One-time pad is nothing other than a bunch of numbers randomly generated, cryptographically safe, and given to you, and only known to you and the server. That's all. No one else knows. And in our case, we use that token every 30 seconds. I think that number it generate a different number, and it is never reused. As per the standard, one-time pad is just one-time use. If it is used only once, the probability of someone finding out is highly remote. This is one of the safest one. But again, now because of all the botnets, hackers have put in all the software and put in millions of PCs. Their little small robo sitting there ready to do the number crunching. So they have thousands and thousands of computers sitting and can do that. So now this is becoming a problem because they will split the keys and send it across to bunch of botnets and get it decrypted, the message. So now I think the people are rethinking about a time. I forgot I am just drawing a blank. A short-lived session key. For example, some of the bank recently started. I think it is not Pulaski Bank or South Indian Bank or something. The moment you enter your login and password, they will send you a text message to your cell phone. They'll ask you to enter a number from that. So what it does is, even if someone try to be in the middleman attack, because you are in communicating through the public network through internet, and if someone is in the middle, someone is able to get your data, you won't get this private session token which is come through a cell phone. They started those in some of the banks. So banks are trying to do multiple authentications. This I have given you, even though it is not part of the whole thing. You will see in many places they talk about this one-time padding. Yeah, RSA. I just now realized the name is Ron Rivet, Hadi Shamir, Linon Elman, 1977. Elliptical curve is very efficient, but it can be the algorithm can be implemented in hardware very easily. So many government organizations still uses elliptical curve for this public key private key algorithm. Many organizations. So if you are joining military and all, they are big in elliptical curve. This also, again, that's if you know the mathematics, you might know. You have one point, two intersecting points. That's what they are trying to do. So these two intersecting points that act as a public and private key, some value. Again, you can research on elliptical curve since you said your background is mathematics. Now coming to our main purpose, I think I gave you a background why we are encrypting data so that people in the middle of the transaction cannot snoop and find out, or some data which is stored somewhere which is not hacked and decrypted and the original message is taken, original data is taken. I gave you a background what it entails to encrypt. So essentially your message is diffused and set in a different place so that when you have the key you can get back. That's the whole purpose of encryption and decryption. So there we covered only confidentiality. No one else can read that. Only the intended person with the key can read that, right? Now comes the transaction security goals. Typically, when you do in transaction security, the goals are, we need to make sure the authorized person, who you say, when Brian says I am Brian, he has to prove, or Mason says Mason, he has to prove why he is. Typically, you will have, there are 3 steps in multi-part authentication. One is what you know, for example, a login ID and password, that is one. That gives you one step. Another multi-part authentication is what you have, for example, your VPN keys. That's what you have. Some highly secured organization go up to the 3rd level of authentication, multi-part authentication. That is, you have retina scan or iris scan or face recognition. That is the 3rd level, because all highly secured. Some of the I used to work in a nuclear power plant, Cook nuclear plant. It's in Michigan. So if you want to get into their inside a reactor, you have to your thumb impression has to be taken, and you have to put there, and they wait for some time. Not thumb, actually the whole palm impression. They really make sure that you are the person, right? So this all makes a person part of multi-part authentication. Again, there are more processes in public key, private key authentication. I am not going to the details, but this, in general, you are not just relying on one value, one processes. What if that process is broken, somebody hacked, and there is a man in the middle? So you cannot. So if you have multiple stages, you are layering your security, you know. So this all you all are familiar with the standard. When you log into a website, or for example bank, you log in and he creates a internal transaction, a validation token given to you, and subsequent to that, every time when you request transaction, he checks, hey, he has a valid token, still you can process that, process the next transaction. He does that. And third stage is you are requesting, only validation, login validation is done, and a session token is given to you so that you can do the real transaction processing. For example, I want to do a payment to Energy Arkansas. How do I do it from my Bank of America? So typically, many banks, what they do is transaction token. They will give you a transaction token. Hey, you are asked for this one payment posting transaction. I am giving you this token. So next time when you are sending it, next second when you are sending it, you have to have this token. Otherwise, I am not going to process that. So once the transaction comes in, he will process the payment and invalidate the token, and typically they write a small little table which will have a transaction token. Till that is completed, he will make it available, and once the transaction is complete, then only you will be then it will invalidate and delete the transaction, so that there is no session replay attack happens. You know, someone has if you don't invalidate the transaction token, someone can take the same transaction and repost it, saying that instead of sending to $100 now, I want to post 1,000 transactions. I'm just giving a theoretical example. It's not simple as this, but I have seen in many banks or many software applications, we issue only a login token. After that, you can do whatever you want, any number of transactions, but that is prone to attacks. You can replay the sessions. So I have seen many banks do that, and now they are getting into trouble. This again pictorial representation of little more details what I explained you. Again, session token as well as transaction authorization, and that this is invalidate. 18. Pardon? Yeah, one is called login token or session token, and second one is called transaction token. I think in our Express, I shouldn't be. We are recording that. Okay, we shouldn't be. Okay, product specific we will talk later. We are recording this conversation. So, yeah. Again, the fundamental approach should be minimize the window of your transaction, because even if someone gets your transaction, first you transacted someone, there was a man in the middle, you are able to get the transaction, and he might go to Amazon and spawn, because you can buy what $1 per hour or 20 cents per hour, you can get a cloud computing infrastructure, 20 cents per hour. Buy some 200, you can crunch the numbers and get those things. So now what organizations are doing, it is the short-lived transaction. You send a very short time, you will be able to transact, because even if someone, a elderly person typing the transaction, he or she should be able to complete the transaction within, you say, 10 minutes. So 10 minutes may not be the enough time for someone to start a transaction through Amazon cloud and get those things, unless they are fully sophisticated. So if you keep the transaction time, validation time within timeout within 10 minutes, even a bank transaction you can safely. But again, there is nothing called absolute security in security. It's all relative. So make sure when you are designing an application, that is the main purpose I called it. Make sure that number one, the transaction session is valid only for a short period of time. Also make sure that once the transaction is complete, the payment is posted, make sure you invalidate the token, even if it's web services. Make sure that you send a null to the transaction, requester. If it is a web-based session cookie, if you are sending it, you can HTTP, there is a flag you can turn on, and it will be available only for that particular session, and you can invalidate the session. So remember that's one of those things, and make sure you implement transaction per transaction. There might be people say, hey, it is going to cost you one more read into the database, one more write into the database. Now the application, that the computers are so fast, you should be able to do, because we have to be very careful about designing application with short-lived transaction, and once the transaction is complete, invalidate the session, which I have seen more than 50% of the application does not do. So again, remember, anytime when you are designing next application, remember, invalidate the sessions. Not sure I want to go in this session. I think we will skip this for now. No? Okay. I think I am cramming in a lot of stuff to you. If it is becoming too much, let me know. Now, in public cryptography, there are two modes which you have to be familiar. One I have explained to you about confidentiality mode. That is, a sender uses the public key and encrypt the message and send it across to the receiver. Receiver uses the private key and decrypts it and becomes the plain text or the message, gets the message. That means only he can decrypt. So that is in the confidentiality mode. No one else can decrypt that, right? Now the other side of the token is you are trying to authenticate. I am saying I am Stellus. Mike is trying to ask me, prove yourself you are really Stellus. How can I prove? I will tell Mike, okay, as per the public key, private key standards, if you encrypt with your my public key, the only person who has a private key can decrypt, right? So you send me a message, hello message. Okay, he only knows that particular message, and he said, hello Stellus, just validate this secret message and send me back. So he writes his message and sends to me, and since he encrypted with my public key, I can only read. I think I am going reverse, sorry. Okay. I am telling him, hey, I am sending you a message to you. Mike, I am sending a message. This is Stellus. I am encrypting with my private key and sending to Mike. Mike uses my public key and gets, oh, this is Stellus. That means what it proves, at least he was able to decrypt the message. That means I am the only person, or at least only the person who had the private key was able to send this. So at least he can safely assume I am Stellus. Now I want to authenticate him. Hey, you told me who are you? I said I am Stellus. Who are you? So there is a mutual authentication we typically call. So I'll say, hey, I want to know you are the real Mike. So I send a short message and tell him, just decrypt and tell me you are. So this is the way authentication is, mutual authentication or single side authentication is done. Question? Oh, wait a minute. Always when a transaction is done, you have your own certificate, such certificate, and you have your own. For example, Ram Babu has Ram Babu certificate and Stellus Pereira has certificate. I have a public key and I have a private key. Private key is kept with me. Public key is published to everyone. Brian knows, Mason knows, all of those, John knows and Dave knows. And that private key can be used in two ways. One is, if someone encrypts with a public key, you only know my public key, right? When you want to communicate to me alone, you will encrypt with my public key. What is the funda of public key? Only person who has the private key can decrypt the public encrypted message using a public key. Reverse is also true. A key, private key, when you are encrypting with private key, only with a public key you can decrypt. So when I have the message encrypted with private key, and you are able to, because I am not telling you anything, public key you are getting from the very sign and say, I want to know what is this public key. I don't want to trust him, even though Stellus says this is my public key. I don't want, because you can do a search on the there is a public key chain. Yeah, so he can do. You can directly go independently and ask very sign. This all happens in your browser. there is a chain of verification, certificate verification process, you will get his public key from, not from me, not from the certifying authority. So then he knows, hey, this is a key issued to me by them, so at least you can trust that. The fact that you are able to decrypt using my public key, that means you are sure by the algorithm I am the person who is having the private key. Understood? Is anyone has still questions, or everyone understood or not? Yeah, validating means, see, when you are getting a message, okay, for example, hey, I have received a message from Stellus. What is this public key? I don't want to trust any other one other than his original certifying authority. In his certificate, there is a certifying authority. You will not directly come talk to me. You will go to certifying authorities and get, because usually what happens, you have certificate cached in many of the organizations. You don't want to go through many places, and so in short, you will get the public key from the certifying authority. So using that, you will decrypt the message and see, hey, he says, tell us the message is right or not. No. Sender's public key is not. When you are transacting, I am transacting between you and me. You are receiving. Your public key is not involved at all. Just I am talking about. You have your own public key, I have my own public key. Yes. It is not. No, it's not same. It's all different for each people. It's different for each certificate. Each certificate. No, then at the whole mathematical form, the very beauty of this large prime number is it has to be distinct from that particular number. No two numbers will be same. Your public key will never be anyone's public key. Period. Similarly, private key. Sure. Yes. Yeah. Yeah. Yes. It will take some time because it took so much of time to understand. But if you remember these two fundas, public key, these two key in public key, private key cryptography, if you encrypt with the message with one key, it can only be decrypted with the other key, whether it's public or private. So you are using that in two modes. One is in a confidentiality mode. I am trying to communicate to you. I want to pass some message to you. So only thing known to everyone is your public key, right? I encrypt with my public key some message saying that, okay, Ram, we'll meet at this place and have something, whatever is there. And when you receive, you will decrypt with your private key, right? You are the only person has that. So confidentiality, no one else can read the message between you and me. Now authentication is is not that straightforward. If you understand the concept, you will understand, because the same concept, the key, the message, when you are encrypting with one key, only it can be read by the other key. Using the other key, you can decrypt. So with that concept, if I encrypt something with my private key and send it to you, and saying it's just a test message saying that, hey, I am somebody, and if you are, the fact that you are able to decrypt with your private key, I mean my public key, that means you are making sure that at least I have the sender has the private key, so we can safely assume that he has the digital certificate. Understood? No, there are two different purposes. This one different purposes. And when we are communicating each other, you will be using when I am sending a message, no one else should read it. What I will do is, what should now I'll have to ask you a question. What should I do? I want to send you a message. It should be in the confidentiality mode. I want to communicate to you. What should be? I am communicating. Stellus communicating to Ram. What should be the key? I should encrypt the message and send it to you, so that only you can read. Anyone? Huh? Say that again. I want to send a message to Ram Babu. So only confidentiality mode, because since I am sending only to you, what should I know? I know only Ram Babu's. I don't have the private key, right? So only option is the public key. Public key is the only one which is known to you. Understood? Not mine, yours. Who is the target? Receiving person's public key. Receiving person's public key. I am not involved. Before doing the confidentiality mode, what you will make sure is, you will go into first is authentication. Hey, is Ram is the real Ram he is claiming. So in the confidentiality mode, we will test each other, mutually authenticate, saying that first time, hey, I am Ram. Okay, prove me. I am going to prove me. Send me your message with your encrypt a message with the private key of yours. I have sent a message to you saying that okay, decrypt and show me. This is not exactly the same thing I am just giving, because this is a very cryptography 101 level. I don't want to go to the details. Something similar to this, but the fundamental is, you are sending a message asking, hey, you prove yourself. You can prove you only by encrypting my message, what I send it to you, with your private key and send it to me back. Then I will say yes, my message, you read it, and I know you are Ram. Got it? Okay. Anyone else has any questions? Yeah, that's it. Yeah, I think that's a whole beauty of this prime number and the RSA encryption. So, you can read on that. I maybe.
Basically, prime number.
It's a prime number.
It's only divisible by one in itself. Therefore, it's not made up of anything. So when you take your private key and help it both one together.
Exponent and mandisa. Exponent and mandisa. I was not wanting to go the detail. The structure of the prime numbers is all large prime numbers. Is all generated. That prime number, you know, the very definition is it cannot be divisible by anything else other than one and itself, right? So it's a unique number. So using that algorithm, what's created. You can read on that. Use a big Mike might be able to give that. Yeah, I think. Yeah. Yeah. No, but it's a pure mathematical function. I think I have the formula. I think I was keeping it for the next session. So he's jumping the gun. I can show you the formula. Maybe I think we'll hold it. We need to have something for tomorrow, right? Exciting. Stay tuned. Yeah, that's the purpose. Again, you have to know the purpose. First, you will not send a message to someone and assume that he is there. So first thing is authenticate. Hey, is Ram or is Stellus, who is he is really claiming? So you have to first authenticate and say, hey, yes, I authenticate you. Now you can authenticate me. Once that the trust is established, authentication is done, then you go for the confidentiality mode. Okay. Any more questions? Don? Jason? Okay, I think we are 20 minutes early then. So my calculation was a little off. So tomorrow we will go into little more details about the transaction security and future trends. In this phase, if we go, we may end the session early. It may not take 3 hours. I was thinking I won't be able to cover the whole item. So, if you have any questions or the handouts as I given you, so if you want reference, again, it's all publicly available information. You can go through and find. Okay then. Thank you everyone. Yeah. Most of the time you hear a digitally signed transaction. Again, remember, digitally signed transaction. So in step 1, if you see you have a document and you want to send it, Bob is having a document and he wants to send it across to Alice, digitally signed, confidentiality should be met, integrity should be met, as well as the non-repudiation. I did not explain what is non-repudiation. Sorry, let me explain what it is. When I send something to Don and say, hey, this is my document, I am signing this document and is as good as I owe you for $1 million. How does Dan know this is Stellus issuing this, or just Mason is faking it and trying to get some money from Don Dinkler? There is no way to do that, right? So in order to prevent that non-repudiation, I cannot say, hey, I did not send a transaction to you, I never signed that document. So in digitally, there is an equivalent for that. It's called digital signature. This is not exactly what is normally done, but for explaining the concept, I am giving you the rough idea. Though, if you see the step number 1, you have a data, and that is taken, and the step number 2, you create a session key. Again, is a random number, cryptographically safe random number based on the key length. Suppose this is a $1 million document, I would say, hey, I don't want 128-bit. I want to go for 256-bit. It will take 200 years to decrypt the document if they have put it on a single prime computer. Or so I select 256-bit, session key is generated, and the third step what I do is take, as I said, any encryption and decryption you need an algorithm. It could be anything. Right now we are choosing AES for the purpose of your familiarity, and you encrypt with the key what you generated, and that becomes a ciphertext, right? This is beyond readable. And the fourth step is, I want to send it to whom? Alice. So Alice's public key is available in public domain, right? So you go and get the Alice's public key and take that public key. Using that public key, you encrypt the AES session key, right? So what it does is this key can be decrypted by Alice private key only, right? So the confidentiality we are achieving by encrypting the data and also making sure that only Alice can read this, right? And the same time, another method I do is take the plain text and go through the hashing mechanism. For explanation purpose, we will use SHA-5. That's as one of the hashing algorithm, and take those hash and take the private key, my private key, saying that okay, I only know what is the integrity of this particular message. I only know I am going to encrypt and put it as a signature value. By doing that, what happens is someone is able to decrypt, will be able to know I am the only person who has the private key only is able to generate that value, right? This is a little complex. I think I want to get to your, again, this is not exactly the way typically the digital signatures are implemented, but only one step is missing that I don't want. There are a lot of things to explain, so for the lack of time I am just restricting to those. Did you understand so far what it is? Sure. Yeah, there are two reasons. Who is the target you are trying to send the message to? Alice, right? So only Alice is supposed to read those. So Alice public key we are taking and encrypting the key, whatever key you had, right? That's a key you want to safely transmit. No one else should be able to read. Understood? So only the person who has the private key, since we are public encrypting with the Alice's public key, only the private key who owns that private key, that is no one other than Alice. She only be able to get the key. The whole game is to secure a key so that no one else reads it, right? Understood that portion at least? Okay. Now you're talking about the digital signature. You have difficulty, or what is what did you not understand? Where is that? No, I am coming to that. It will take some time to sink in because I took at least a couple of months to understand. I think everybody is smiling. Yeah, it will take some time because unless this preliminary function in your mind settles right, you will not be able to do this process. Remember, these two keys has two different purposes. One simple thing if we can remember, that is a key, private key, a data encrypted with public key can be decrypted with the private key. That is number one. And reverse is also true. If you encrypt with a private key, only a public key, the person who has public key can be decrypted. I think is too much to take in. So let's do one thing. We will. Sure.
Okay, so since the private key is the last thing to sign,
Uh-huh.
how does Alice know that it's supposed to be Bob's public key?
Yeah, we will come to know that. Yeah. When the second side of the equation is not shown to you, I want you to sink in the first process of encryption. Anyone else has question? Go ahead, Dan. No.
So in the flow, the RSA box,
Okay, which one? This one or this one?
there's two of them.
Okay.
So if I'm understanding the flow is going to go through there.
This is which number? Which number?
Let's see. That's
4?
number 2, the session key.
Okay.
The flow goes down to the RSA box.
No, there are two things happening here. One is, I think I should have made it a little more clearer. The data is, the message is encrypted in the step 2 using the session key. As simple as that. So that is essentially you are making this particular data not readable to anyone. It doesn't matter whether it's Alice or anyone who does not have a key. Who does not have a, if you don't have a key, you cannot read this. If the key is derived, anyone can read this. Now here there are a couple of things happening. One is you are encrypting the data as well as exchanging a key to the receiver, saying that, okay, I encrypted this data and this is a small little secret, I am hiding it here. And now how do you hide some data? Best is encrypt with your public key so that only you can read, since you only have the assumption is you only have the private key of those. So that key exchange is done through this step 5. This the whole data is ready, and now when you go to the second stage decryption, you will understand the whole thing. But I don't want to give you the second portion now, so that at least your mental process starts and how things works. I want you to really sink in, because this is the most important part, which most of the classes I have seen they missed. So I keep them some time. So if it is okay with you guys, and if you don't have, go ahead.
Number 2 to number 5 you have drawn what the number
2 to 5. Okay. See, this 2 lines actually should be broken here. The step is not the go through of individual lines, it's the steps you have to follow. So the second step, the process is creating the session key, and the third stage step is encrypting the data with the key here. Yeah, here it should end here, I understand, but I should have changed that. But the third one is the same key is used here. I think it's a question of drawing the picture right. Yes, you're right. Let me correct that. Is that okay now? At least, so there is a split, right? Or does anyone have still confusion? You're okay? Okay. No. We are sending Bob. Bob is sending a message, to digitally signed message to Alice. Yeah, there are 2 purposes of session key. The main purpose is to encrypt the data, right? Randomly at that particular moment, the instance you want to send the data to someone, you want to generate a new number. It's a long number, 256-bit number, which is for block ciphers is pretty safe. Block encryption, not block encryption, I mean symmetric encryption. And since you encrypted, you have to tell Alice, hey, I've encrypted this message, but if Alice does not have a key, how will she decrypt the message, right? You have to have that. That is going as a part of this message as an encrypted key, because if you put it in the plain text, anyone can read, right? During the transit, man in the middle, someone can. No, there are separate blocks of data. That's why I gave 3 colors. 2 processes, yes, is not same. That's why I gave 1 by 1 step, saying that, okay, this is what happened in the second stage. Third stage, you go this data, and fourth stage, what happens is getting the public key and encrypting that particular, because the reason is I want to send this key which is only available, readable to Alice. So we are encrypting those with her public key. Only the person who has the private key will be able to read. Alice's private key only Alice will have. So I am putting it here. And why digital signature? Because any text, as I said, hashing function has a very useful feature. Even one bit of information is changed, the hash will have a different value. So that at least we know during the transmission, someone, man in the middle, took the whole thing and just changed something. Instead of, hey, I'm transacting $100 and he changes it to $100 million. If there is no hash value, there is no way of finding out, right? So in this transaction, the message, if one bit is changed, your MD5 or SHA-5 will have a different number. So that's the way you are enforcing the, making sure that the integrity of the data is not compromised. Okay, I think it is a little too much. We'll take a 10 minutes break. Okay. Oh, go ahead. No, well. Again, 3 times you are doing encryption. I understand. Yes, 3 times you are doing for different blocks of data. One is the data, the real message. Second one is the key. Third one is the signature. Yes, 3 times you are doing some kind of an encryption. If there are no questions, we will meet after 10 minutes. So since you had a break, I thought your memory is kind of settled, ready. Still something is lingering on your mind. Can we go to the next? We go to the next process of decryption, or it's going to be a little heavy on the screen. Okay. Okay, once the encryption is done and the key is secured and a digital hash is created and the data is transmitted and Alice receives the data. Alice cannot just directly read anything, it's all garbage, it doesn't know anything, right? She has to get the key, right? She looks at the encrypted key, which is encrypted by Alice's public key, right? So she has the private key store, she pulls up his, it's only available to her, reads and decrypts with that key, she gets the AES key. That's the first step. So she derived the key, right? Are you still with me, or are you just shaking hands because I am just saying it?
The corroborating private key to the public key that
Yes. You're okay with that? Okay. So once the key is derived, she takes the data, encrypted ciphertext, and decrypts with the key. Simple, right? So she gets the actual message. This plain text, she gets it here by the step, I think it is called 5. Yes. Now she wants to find out during the transmission of the data. Hope I have started this out. Sorry. Okay, it's recording. So, Muthu, come in. Yeah, this is a crucial place, I think. For Muthu's purpose, again, I'll re-explain explain again. So once the whole packet signed, digitally signed data packet is ready, Alice gets it, and she looks at her private key because that's the only person who has access to that. Gets the key and decrypts the message, that AES key, whatever is being created by Bob. She derives that, gets the key, decrypts, and use that key to decrypt the message, because AES is what the algorithm he used, Bob used to encrypt. So use the same algorithm to decrypt, and she gets the message. Now she want to know, during the transaction, in the middle someone was standing and changing the $100 to $1 million. There is no way to know, right? So what is the best method to know that? What did we learn? How will you check the integrity of the message? Excellent. So she, on the fly, she computes the plain text message MD5. It is in the packet itself. It was a protocol saying that, okay, I have used MD5 for the digital message digest, so use the same. And she manually creates, not manually, using an algorithm, locally creates the MD5 that I am calling it as message digest 1, right? And the next step, what she does is, this is the sixth step, right? Fifth, sixth, seventh step, what she does is, she looks at the digital signature, pulls that data, and that data is encrypted with what? Bob's private key. So what can be decrypted? Only by public key. That means only private key has been using. He has used private key, so obviously public key of Bob, which is available to Alice, she goes and decrypts that. So that tells you two things. One is, you will get the right value. If you get a wrong value, that means it is someone else acting as someone else, not Bob. So you get the message, you are able to get a MD5 value, and you are comparing those, whatever computed locally from this message and what has been sent by Bob's through the digital signature. So that if it is matching, that means there is no integrity, as no one has changed the message during the transit. Any questions, or still I prepare some base so that at least you get the left hand side of the equation, at least you are comfortable. The same thing you are doing in reverse here. You're okay with that? Okay. You? Ram Babu. Again, I'm going to call Dave Dingler. Sorry, I've been calling him Don. somehow I made a mistake, and standing here, things, your memory get parity errors and all those things. You have any questions, sir? You are looking. You are okay? You? Yes. You are okay? Comfortable? Okay. Now, this covers about transaction security. How, when you are signing a message, you are transacting between two parties, confidentiality, integrity, and authenticity. These three things are primary three principles which has to be covered in any transaction. This can happen only if you have mutual authentication, because you have to have both the parties, communicating parties have to have certificates. It can be a self-signed certificate, but then authenticity is cannot be verified. So in a digitally signed transaction, you have both the parties have to have certificates to have integrity, authenticity, integrity, and non-repudiation. He cannot. Now, the non-repudiation word I keep repeating. The reason is he now cannot say, hey, I did not send $1 million transaction, because you can tell him, hey, you send me this digital signature which can only match for that $100. If something is changed, this signature will not match, right? And we can be sure only the person who had the private key had the capability of signing the message. Karen? Yeah, hashing the key collation. That's why I think I said, okay, if you are your message, I think there are key collation in MD5, but it is for a almost, I think, more than 10 GB data. When you are sending 10 GB data, one bit is changed, because this algorithm will not take care of it. But typical transaction wouldn't be having such a large data unless bulk encryption. Collision can happen. I am not saying it is going to happen, but at the same time, many things has to be in sync to happen that. Same data, yes, collision can happen. So in the message, such a way that from just $100 to making it $1 million and keep the same hash, you will have computing time a billion years. By the time Earth will just smash into sun, I believe that's the prediction, right? Okay. So if there are no questions on this, then we'll move on to the next item, which I promised will cover some future trends. This has nothing to do with the transaction integrity, but at least I want to give you what is happening currently in cyber security. I believe in 2001 there was a consortium formed called Trusted Computing Group. Why it was formed was, even now there are a lot of malware getting propagated to many PCs, and they are taking over the world. And the main reasons are, there are hundreds and hundreds of ways of propagating the malware, through emails, through websites. So because of which there are millions and millions of computers are infected. Trusted Computing Group has been formed, and they came up with some proposal. They proposed a structure in which, how can you minimize, you cannot eliminate, minimize the infection, number one, that is a primary criteria, and making sure you are doing the computation in a trusted platform. The environment, the base environment can be trusted. So in order to achieve the trustworthiness, they suggested few things. I think you can search on the Google and find out trusted computing group. They will tell you what all the specifications. It is still in progress. And also from the cybersecurity industry, there are next generation intrusion prevention systems generated. Cisco is a huge player in that. HP, IBM. One of the very popular intrusion prevention systems are, I think it's called SolarWinds. This, I think one license for that costs something around 35,000 per year, which essentially monitors, not really monitors, goes through piles of data and pinpoint, at least to a certain extent, where all the vulnerabilities, whether it's what kind of attacks are happening, who is stealing what data, those things. So there is third generation, next generation IPS systems being developed. And also Cisco came out with a deep packet inspection tool. Now I am going to network terminology. Anyone who worked in computer networking, any experts? No? Huh? Yeah, that is only. Yeah, okay. So you know firewalls and bridges, routers, and all those things. Yeah. Most of the security professionals, at least in the network, they don't like to do deep packet inspection. Deep packet inspection means when you look at the data going through your network, there are millions and millions of packets running through your network based on the bandwidth, whether it's T1 line, OC3. If you start analyzing what is going inside the packet, you need lot of computing power. That was the concept till 2001. So what people use, they used to do only sampling wherever you have some suspicion. If you see a non-standard transaction, something fishy happening, because you can define some rules and find out to a certain extent, and tag that transaction as a vulnerability, a suspicious activity, and either you can chuck him out of the network, don't allow them to all the IP, block the IP addresses so that they don't come in, or prevent them next time coming into at all. So that needed a lot of computing power and network bandwidth. So now, because of this big data framework, I think you all must have heard about big data. Using your consumer PCs, or you can farm all those processes, chunks of data, and send it across to multiple PCs or servers, and assemble those and do deep packet analysis and try to write some rules using some rule engine and analyze. That's one of the new trends which is coming in, because how many computers do you know we have? Whole network, US and Mexico and Europe. Any idea? Yeah, there is only 100,000 employees you're talking about. Okay. Yeah, but about okay. Also, do you know the percentage of utilization of the computers? Say that again. No. The percentage of utilization in average, all the PCs. Yes. And some are just only playing solitaire. Sorry, I didn't say that. Sorry. So you can utilize the free CPU processing capabilities of all our PCs. Only what you have to have a small layer which you will receive when it is not doing anything or playing solitaire, should process those transactions and report to the central unit. That trend is happening because no one wants to spend any more money on buying new hardware because it's available and not being used. So there is a tendency for many of the organizations coming up utilizing the existing infrastructure when it is not being used. That is one of the new trends. Brian, I think in our batch processing we should think about doing that. I think we can farm all those things to many places. So our guys, huh? Yeah. Yep.
By the same token, malware on all those PCs is also tracked faster.
Yeah. Yeah, obviously you have to take care of those things. Yeah, you cannot process customer client NPI data on the PCs. I understand, but at least network traffic analysis at least it can be done.
Are there any current metrics on like AES based on how quickly that can track?
Yes. I think in the previous yesterday's session I went through that. You can go to Amazon. I think now per hour for a quad-core i7 processor, it's only 24 cents, I believe. You can get one small hour, and there are people doing that, cracking those, and it could be because one of the slide which I mentioned. Based on the availability of Amazon cloud and computing power, we said we should never allow a transaction to be more than 10 minutes, because within 10 minutes the even private keys can be cracked if you have some, assuming that you have something around 500,000 machines if you can buy. That depends on how, if you are trying to crack only $1,000 transaction, it is not worth. If it is $1 million, yes. Yeah. That is one thing, and so I was talking about, because of the challenge came from a trusted computing group, Intel has come up with, Intel as well as a couple of other companies came up with a hardware chip which has some unique capabilities. For example, if you have a rootkit installed, again I am using a new word, and let me explain you rootkit. Rootkit is nothing but some malware lands on a PC and takes over the whole control. That is, even before booting, that boot sector get infected and the malware sits there, and he has the control of the admin, so that anytime when you are trying to do a public key private key, everything will go through his. He can change the API and get your transaction between the operating system and your simple application. So rootkit is one of the biggest problems. So in order to prevent rootkit infection, this is one of the reasons they came out with this trusted platform computing, so that at least the bootloader is not corrupt, because that's what typically rootkit goes and corrupts the bootloader. And if you cannot keep the integrity, or you cannot verify the integrity of that particular program, everything is up for grabs, right? He sits there and you say MD5, I am expecting 234 CBA, and he knows that this is the last transaction he sent to us this, so give him this, right? So integrity of that data you cannot verify if you are using a standard API transaction of Windows or Linux. You know what I mean? So if something is embedded inside the operating system between layers, all your security is off, whatever you do. So the TPM chip has few features which essentially gives you three facilities. One is secured booting. So at least it will make sure the boot image of your operating system is not corrupt. Also, sometimes it is called measured boot. There are two different competing groups working, TPM and UEFI. Essentially, there are two different approaches for preventing those malware infecting your system and making at least not a non-trusted platform. So Intel has come out with, I don't remember the name of the chip, but the functions, primary functions or modules of trusted platform modules are this. What you are doing in a software, it is done inside a chip, so that someone infecting, because it's a secured chip, if you try to break open, you cannot get the keys. There are still, people will try to break it, but since it is a non-volatile memory, a virus cannot or a malware cannot change those values, right? So when a PC is manufactured, you have certain keys already stored in the burned into the chip, which will match your operating system MD5. I'm just giving you some. It's not exactly the boot sector's MD5 value will be stored, so that at least you can make sure that you have the same values, which cannot be changed by any software. So even someone from China bombarding you with some software and corrupt your operating system, during the secured boot process, he can throw you out. So TPM chip has functions, crypto processing, encryption, decryption standards, and MD, message there is nothing but hashing. Also a random cryptographically safe random generation function. But that also, because when you want to do encryption, if that is being done at the operating system level, someone sitting in the middle can get the number, right? The whole strength of the encryption relies on the key, right? If you can get the key, the whole game is off. Also, it has a private key, public key generation process. So it is self-contained, it doesn't have to depend on anywhere else. When it is in the software on your disk, someone can go and change the entry and exit point. Okay, when you are calling API MD5 with my data pointer, in your memory, when you call, if it's not infected, you will get a value properly. But if it is infected by a rootkit or any other malware, he can reroute your transaction, take the data, and give you the whatever value he was expecting you to give to you. Is it difficult to understand, or you are still with me? You're okay? And I'm not going to go through all the items. Essentially, we can store the values burned into the system. Also, there are some ways for servers remotely authenticating from somewhere else, because in a typical servers, this information has to be available, attested by a higher authority. So what it will do is, it can even authenticate, okay, what was the stage yesterday before when you booted the system, you had for the boot driver, you had an X MD5. Other drivers, you had different values. That value can be checked by a third party, a server remote authentication process, and tell, hey, there is something suspicious on this particular machine, so let me shut down. This was the third thing which trusted computing group suggested, because infection can happen anywhere. How do you isolate? Only this guy is having problems. So one way to prevent this, having those values and check the integrity every time when you reboot the system. At least you can ask for it, or even while it is running, the remote authentication system can attestation system can ask, hey, what is your number? Right? Tell me your boot's this number. I want to verify. You communicate with that particular machine's private key, local public key, and so that only the private key guy can give you the result. So that is the third thing what they have recommended, and people are implementing. Then some of the in fact our I think it is a Dell laptops has some TPM chip. I don't think we have enabled. I think there are some Windows 8, I believe. They are trying to make this mandatory or something like that. I'm not sure which operating system. This is TI chip, I believe. One of the Infineon. This is a trusted platform module. This is a real chip which is being, I think last 5 years it is out in the market. In some of the computers they use that and start using it, mostly used in servers, but as a standard I think Windows they are trying to say, I think by 2020 or something, all the operating system when it is installed, you will have those chip, and the operating system bootloaders digital hash will be stored. And the industry started yelling and screaming when the update comes in, how do you do those things are weakened. Yeah, but I think Linux on it. Yeah, no, Linux will also have their own operating system number so that you can verify. They cannot lock down those things, but at least those numbers are safe, so that at least that process is safe. This is the process which Trusted Computing Group recommended. So when the server or PC is booted the first time, it boots the BIOS kernel. Before booting, it will check what is the message digest, and is it matching. It will ask for what is the number here for that particular signature, and before booting it will compute the MD5 and see, hey, this file system is not showing the right number, I am not going to boot. He will quit from there. If that is successful, if it is matching, he will go to the next boot, BIOS, bootloader, then kernel and early drivers. See, in this stage anything fails, it will stop there. So by doing that, what is achieved is malware infecting your operating system or kernel, the drivers can be prevented. Again, you cannot have thousands and thousands of softwares, MD5 digital signature and store and compare, you cannot do, but at least it will make sure that the basic operating system is not hacked. That is a current problem which can be minimized using this process. Now, as I've been mentioning about these botnets, can someone want to share about botnets, their experience or anything which I think anyone want to, from the participant, what do you know about botnets?
In Michigan State, we had this department web server that was exposed to the public, and we would look at the logins, and you could see the server the performance would be great, and we would go and look at the logs, and we could see that there were login attempts with common login names such as administrator or web admin, or, all the what you commonly think of might be a web address, and you could take the IPs that were coming from there and you could trace them back, and they could be
anywhere.
Usually they were from just a commercial ISP or residential ISP services. They could be from California, could be from Estonia, they could be from Korea or China or anywhere else, but very rarely did it ever trace back to anything that wasn't a commercial IP, so it was infected zombie machines that were getting it.
Anyone else? What is that? I did not see the movie. So they say Evil Eye. That's a movie, or I didn't. In someone, I think FBI is have one particular division just working on this art botnets, because that is a huge threat to the world's computing infrastructure. For botnet herders, because there are some terminologies I've used, they get free CPU cycles. It's available on their command. Once the machine is booted, he can send. Once it is infected, what happens is he will report to a central command. That's again, and say, "Hey, I'm up and running. My CPU utilization is only 5-6%," and then sleeps there, and tells you the IP address and the routes he can come through, alternate routes or those things he'll publish to him. And anytime someone want to, for example, Bank of America website, they want to attack, just one click of mouse, they can send you all the active. For example, Chicago, you have a bank and you want to send a massive amount of transaction. They can geographically locate, isolate, and say, I have the closest to Chicago, all the Illinois, state of Illinois and Indiana, attack all the botnets. They can send millions of transactions. They can overwhelm the whole internet. So that is a big problem. I think there is a cybersecurity force constantly working on those threats and trying to mitigate. And also this botnet guys sell CPU time. You can compute. They have some infrastructure to compute. To commercial organization, hey, I want to do some design simulation. Okay, heat flow analysis of a car's engine. You need teraflops of. You don't. If you really need to simulate, you need supercomputers, Cray, XMP, YMP, all those machines. So for a short period of time, I want to compute certain mathematical simulation you want to do. Pay X amount of money, they send all those transactions to all these botnets, get the transaction done, compare it and send back. It's a big industry. Because if you go and you look at your PC itself, take your laptop and see how much is your percentage utilization now on an average. It will not be even 20, maximum 20, all for developers like us, it won't be even 25% because the rest of the time is not utilized. So what do they get? Free CPU, waiting army, zombies, anytime they can attack or do brute force decryption. And they have, one of the good thing is their designs are so fault tolerant, they don't assume anything is working. If one machine is working, good enough, they will work on it. If you have 100 machines, it will still work on. So their designs, I think, in fact, we should learn from their system because we are not able to come up with our own. We have so much of infrastructure. We are still not having success in getting those kind of sophistication, fault tolerance. Simple web sphere goes down just because of null point exception and uncatch exceptions, right? You are all familiar with those things. And so they are technically really, really sound. And they are highly motivated, right? The current stats is the most popular botnet is called ZS. In US alone, 3.1 million PCs are infected with the ZS. Similarly, Coopface, Titserve, they have some funny names. So imagine average, the computer, I'm saying the life of a PC is, you say, 5 years. Most of the people keep. Average computing power per PC is almost 50,000 MIPS. CPU, Intel even mentioned about your Core i5 or. And imagine that into multiply by 3 million. How much is the CPU power you are getting? Much, almost I think 100 supercomputers, which is really useful for someone who want to really good damage to the. They can attack Pentagon or no. This is not directly related to our transaction processing, but I think what I have seen is password storage issues. I don't know any of you are familiar with that. When you store password, most of you understand, you don't store the password in clear text, right? So what do? You create a hash, either MD5 or SHA-512, and store that value, so that at least someone just coming and looking at that, you cannot derive the actual value, and your algorithm takes care of comparing. When you say Stellus password is password 123, right? The easiest password, so you can crack it. So it creates a hash and compares with your database and what is the hash MD5 matching, then you allow you to transact. But there is a big problem. What had happened is people started storing common passwords. There's a known dictionary attack, known password you can attack, and also they came up with all the permutation combinations. MD5 is a popular algorithm, and SHA-512 also is an algorithm. So what they did is they started creating a full database or tables called rainbow tables. So I think terabytes of data is available. What they do is actual value. For example, Stellus is the name password, and you can have only one unique value for that MD5, right, or a SHA. So they compute for these two values and store it somewhere. This is uniquely available. Admin will be admin for any computer, right? MD5 if you are using, providing that. So they, using massively parallel processes, they started creating all, come up with the data. You can, for I think it is around $40, you can get the DVD. They will send you that with I think it is 8-byte all the permutation combinations. They give you the MD5 and SHA. So if I know what is the number stored in your database, the password MD5, I can crack that. Simple. Are you getting my point or no? See, you are storing not the plain password on your database. You cannot, if you store it, it's easy to go and look at it and go from there. But if you are storing, for preventing those, they started storing the digital hash of that value. And now since a rainbow table is available, just match the digital hash and get the actual password. This is called rainbow table attack. So the industry came out with a solution to that. You add a salt before generating the password. For example, my password is Stellus 523 some number. That's my actual password. So before storing the password, he's writing my password. No, that's not my password. Okay. He works with me sometimes, so he can crack my password. He's a smart guy. Sorry. So what it does, what you do is, the issue is if you are storing, you have the password, you are storing the MD5 value always, right? You say 75 B C D E A. That is your, I'm just giving you it. This is the value which is, assume that my password was Stellus 023. and you have an equivalent MD5 for that. And suppose in the rainbow table already when they created, because they are trying all the permutation combinations for a 8-byte password, right? They already created, so Stellus will be there present. Once you get this 75BCDEA, what is the equivalent Stellus 023? I can log into FIS account. So that is broken just because of the rainbow table. So in order to prevent that, they came up with the salting a password. They used a fancy name. Essentially what it does is, when before storing the password, you add a string, which is the middle or split, whatever is the mechanism, which is known only to your cryptographic libraries. So unless this salt is known, the hash function will not work. The storage, even if you get this is not equivalent to what it is there, the password coming from the user. So once you add the salt value will be something different, right? This is not this. Now your library has to take care of getting the password and adding the salt and recomputing and checking which one is the right one. You know where I am going with this? Essentially you are not assuming storing the same value as the password's hash. You are salting it, changing it, so that without having both the values you cannot derive this MD5, and from the MD5 you cannot derive the original, because again in hash, what is the primary concept? You cannot derive a value from the hash value, the original text. This I am giving you because I have seen in some of our previous versions of. Another problem with current infrastructures are hackers are highly motivated. They get run for the adrenaline, right? They want to hack America's hacked, so they are highly motivated. And big organizations, there's few PCs unpatched is good enough to penetrate inside. Once you are inside the network, you are done. And always you will have a weakest link in our system which can be exploited. So people are sitting and scanning what is the IP address, what services are running, what operating system the PC has, and goes and finds out what is our vulnerabilities and send a vulnerability matching those and exploit the PC and take over, install rootkit and take over. Those all are the current problems, and one of the classic example happened in Afghanistan war. Someone left a USB drive in Afghanistan, the military base. The soldier took it and connected to their PC. The whole thing got, imagine, just not even what $5 USB drive, right? See, imagine how much damage they can do. They took almost, I think, 14 months of cleaning up those. So security you have to take really, really serious. That was one of the motivation, me educating. You know, we get a lot of flyers, email, you get all the compliance classes, you have to mandatory classes, all those things you have to do. But unless as we are the gatekeepers, you design software and that software can be hacked and utilized for purposes which is not intended. So you have to be careful of those. Now, just as a personal, this has nothing to do with the organization. When you are connecting to internet, whether using your iPhone or your iPads, there are certain algorithms used for handshakes use, which is all, there are some vulnerabilities. You have to be careful when you are connecting. One of the things which I want you to turn off in your iPhone or in your iPads, make sure that you don't auto connect to your known access points. So in your home you might have, okay, wireless access point Brian, you have a local access point you define. What the hackers has found was, because when you are searching for, when you start the machine or your laptop or iPad, it starts looking for that particular access point. So while scanning, you can find out, oh, there is one access point Brian always uses. It is his home PC that he is trying to connect, even though he is in Chicago airport. There's a small little device, I think around $20 or $40. There's something called Pineapple. Have you all heard about those? No. It is nothing but a silly access point. What it does is, it act as your home network access point. When Brian is in Chicago, so Brian home 123, that is the network design. So he is sending a transaction, checking, is Brian 123 home available there. So the Pineapple can see, hey, there is someone with this particular name. See, let me giving me a fake point. So when you are doing that, the first handshake is you automatically send your ID and password for that access point. Because I say, hey, my encryption key, okay, let's communicate with a key pair. I am giving you this, and you don't check. Automatically, it gives you your user ID and password. It doesn't connect. He got the password and got, right? It can be used to access your network, provided he is in that area. But what I'm saying is, there are a lot of vulnerabilities. So one advice to you, when you are in the public network, never log into your first of all, turn off your auto connect. Look for a specific network which is trustable and connect to that. Pineapple is becoming a big problem. People are stealing the user ID passwords and publishing to the whole world, and it tells you which location, because your IP address is almost tied to a geographical location, right? Sorry, something is happening. Huh? Oh, okay. Pineapple, huh? Okay. Uh-huh. Yeah. Yeah. So, common sense approach, make sure your PC or a laptop is working in harmony. So always make sure you patch, keep your operating system as well as the applications patched and up to date, current, so that at least there are less vulnerability. I am not saying there is no vulnerability. There is nothing called no vulnerability. Make sure that that is done, so that at least malwares, rootkits are not infecting and you becoming a part of the botnet community. With that, I will, you know what is man in the middle, right? Or what typically in man in the middle operation does is, you know, in the networking, I want to connect to a particular server. You'll say blah 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 and a server, and it has a particular IP address. When you querying the DNS server, it will tell you, hey, for this machine, this is IP address. But in the man in the middle can for a short period of time, hey, I am this particular server, just communicate with me. Within a short period of time, you can do that. There are prevention systems, but that can happen. So that is the way he reroutes the transaction and gets your password and get your $1 million from your bank, because he will provide you a fake certificate and you can have a reasonably good handshake and take the password and send it across. So he is sitting in the middle and watching all the traffic, taking all your credentials. When you get the credential, he can use that, right? The man in the middle itself is around 2 hours of explanation. I am not going to go through that. I have material for that, but I think this concludes most of the stuff. So if you have questions, we can go with that. This is a cartoon I like very much.
But one thing I've seen in working on DM, our passwords are stored encrypted.
MD5.
When I'm debugging through and I'm working on them in memory,
Yeah, it will show that. Yeah.
there's my password. It's just an encrypted text stored in memory. Is
Yeah.
that a security concern?
Yes, it is. There are certain type of data type only we should use. That is one of the part I think we are still currently working on. My thing is security is the last. So I think slowly it will change, and it's all we have to convince the project managers the importance. When you try to convince it doesn't work, and when the client demands, it will work. So I think clients are demanding. I think you might have some input. Do you have any inputs on that about the securities, or do you work on security, or?
Yeah. So every, I know Pepper was talking about the yeah, absolutely. We have to talk with clients.
Do you all use FRAP library or no?
We do use RAP. I mean, on that specific issue, so the new
Suite, 45 suite, okay.
the new patches will identify passwords and things like that that are not stored in
Clear text.
fields in memory. In .NET,
Mm-hmm.
not stored in memory. Default value is, but then you can also alternatively, almost like the digital signature type encryption payload,
Okay.
field level encryption on an individual password field, so it's passed around the system. It's always being passed, encrypted, or whatever, but that field is always passed around encrypted, and then at the point where it actually encrypted at the time. Clients will always throw up a scenario if, it comes up in tablets a lot. If a guy walks out of the field tablet or you report a crash or something like that, they want to, in theory, somebody can get a connection to it over the memory. If they can find it, they can find the password. But preventing it completely hiding that password in the process is incredibly difficult, especially with garbage collectors. But we can get a lot more than we are today.
Yeah.
Eliminating it is possible.
Yeah. Also, one of the things which we found to us, Unix and as well as in Windows, there is a paging mechanism, right? What one of the attacks are, the malware will generate tremendous amount of transaction. You'll generate so much of transaction, it will fill the memory. The moment it fills the memory, what happens is, as a standard, it will swap into the page, and that is not encrypted on the current, at least Windows. 2010 till 2010 it was like that. I think I don't know about Windows 8. Linux and Unix also had the same issues, because that is available to anyone. So those things are still being worked out, because that is one of the vulnerabilities. You just jam so much of transaction to then create a memory overload, fill with the memory. The moment is operating system automatically pages that into the page which is available. So there are many vulnerabilities, but people are working on it. So that is one question. And any other questions? If there are no questions, I think we are early, but I would need your feedback forms. Would you mind at least completing that and giving to me? Again, name is, see, the purpose of feedback is for me to improve the content of this course. This might be, I might give to, there is already some talk about a detailed cryptography session going for 4 or 5 days program, but I want your feedback. It is not to praise me or something, but the purpose or the intent is to improve this course. What you liked, what you did not, how can you improve? If you frame that, is good enough. And before starting the course, I forgot to tell you, I'm from India, you all. The word we will have difficulty in understanding me, because the word choice we back in India is different from American word choices. Also, I have an Indian accent, so certain words I pronounce, or most of the Indians pronounce in that particular way. So Americans find this difficult. I should have told that. Anyways, never late, I think, to tell those. You can give it to me, or you can keep it over there. That's good enough. Yeah, you are the first person. Thank you. Again, the purpose is to improve my content and the delivery method, so focus on that if you can. Yeah, just going to stop that.